In this video, we're going to illustrate the POP instruction on the x86 64-bit architecture. In another video, we described the related instruction push. These two instructions are an important part of the interface to the runtime stack. Our video on push contains a review of the structure of the x86 memory, so we won't repeat that here. If you're confused about any of the topics of byte addressable memory, storing multi-byte items into memory, or big-endian representation of data, then I suggest you view that video. Recall that in the x86, the runtime stack is just a contiguous region of memory allocated for this purpose. The stack pointer RSP is a 64-bit register that points to the top element on the stack, meaning that it holds the address of the topmost item on the stack. If that data item requires multiple bytes to store, the stack pointer holds the lowest address of any byte in the block. The x86 stack goes downward in memory toward lower addresses. Thus, when an element is pushed onto the stack, the value of the stack pointer decreases. So when an item is popped off the stack, the value of the stack pointer increases. Now let's describe the pop operation in more detail. Pop is a unary operation. That is, it takes a single argument. The argument can be a register or a memory address. The semantics is to remove the topmost item from the runtime stack and load it into the argument register or memory location. Note that it's possible to pop different sized items from the stack: 1 byte, 2 bytes, 4 bytes, or 8 bytes. These are differentiated in the x86 assembly language by adding a suffix to the pop operator. For example, we'll use pop L to pop a 4-byte quantity and pop Q to pop a quad word or 8-byte quantity. If the destination is a register, its size should be appropriate to hold the value popped. If the destination is a memory address, it's simply the address of the first byte of the destination. For concreteness, let's assume we're popping a quad word from the stack into the 64-bit register RBX. The command we'll use for this is popq RBX. Let's also assume that the stack pointer RSP contains hex value 118. That means that the current top of the stack is at location 118. That is, whatever the current topmost item on the stack, it's in the block of memory whose lowest address is 118. And by the way, there's nothing in the machine state that tells us how many bytes that topmost item on the stack occupies. The compiler or programmer needs to keep track of that. Finally, let's assume that the relevant portion of the stack is as shown here, where we've indicated the stack pointer with an arrow. Now we're ready to execute our command, popq RBX. We don't really care what's currently in RBX, because we're going to overwrite whatever is there. Execution of our pop RBX operation happens in 2 steps. First, we copy the 8 bytes of data on top of the stack into the destination register. Since the x86 stores data in memory in little-endian format, the byte in the lowest address, 118, is the least significant byte. That has to be reflected when the bytes are reassembled in the register, but don't worry, the machine will get it right. Second, since we're popping an 8-byte value off the stack, we must increment the stack pointer by 8. We increment since the stack grows toward lower addresses. In hex, the new stack pointer value becomes 120. Notice that the byte values popped are still there in memory, but now they're above the stack. The other variants of pop execute in analogous fashion. In this video, we've described an explicit pop instruction, but there are important other ways in which values get popped off the stack. Most notably, a subroutine call instruction causes the 64-bit return address to be pushed onto the stack. Then, when execution of the subroutine reaches the return instruction, that value is popped off the stack into the program counter. That happens exactly as if an explicit pop had occurred, as we've illustrated in this video.